Today we have the pleasure of having Édouard Oudet, who will speak about metric optimization in spectral geometry. And the floor is yours, Édouard. Thank you.
Donc, bonjour, bonsoir à tous. So, thank you very much, Alexandre and Jean, to give me the opportunity to present my work. Today, I will present some results related to metric optimization in spectral geometry that have been obtained in collaboration with Chiu-YenKao and Braxton Osting in the last years. So my talk will be divided in two distinct parts. Actually, the first part is related to the isometric embedding of surfaces. And you will see that I will explain all the context based on some previous work which have been done in the HEVEA'sproject group. So I will present what they did. I will present what was their approach, and then I will introduce what we did with the Chiu-Yen and Braxton. And in the second part, I will discuss what we obtained more recently, investigating the numerically again, investigating the link between optimal Stakeholder surfaces and minimal surfaces. So this subject is relatively well known in this community, but as far as I know, very few has been done on the numerical part, and you will see that some specific difficulties appear when you want to approach this kind of objects. Okay, so let's start with the problem of isometric embedding. So as I told you, my main interest is in scientific computing, in approximating objects with a computer. So I will, since this community is not specialized in numerical analysis, I will focus on give you a complete description of the background of the subject, and just a few details of what we did and what we tried. But you will not have a lot of numerical details. But if you are interested, of course, I would be very happy to answer questions. So what is this first subject, which is the problem of the isometric embedding? So first, I define in a very classical way what is an isometry. So you have a surface, a Riemannian manifold of dimension 2. So in all my talk, I will only speak about two-dimensional objects. And I'm interested in mappings, which are bijective mapping and which are isometric. So that is the length on the surfaces are transformed on curves. So curves in the surface S are transformed by this mapping in curves of the same length, essentially. And I will focus on isometric embedding of a surface in R3. So we are in Grenoble. We have very good theoretical mathematician, but we are very strong also expertise in experimental mathematics. And so I want to introduce this experiment, which has been done by Thibert, which is one of the guy of the project I just told you. So this is the experiment. So you just start with the torus, which will be the flat torus. You all know what it is. So you want to associate opposite sides. And so if you do that with a piece of paper, then you are able to recover the periodicity of the picture. But then in the last step, if you want to glue together the two red circles, then you get into trouble, not really troubles, but what you obtain is something with you obtain a bending of the piece of paper, which raised the question of how can you do that? How can you embed it, the flat torus, which is an example of a Riemannian manifold, into R3? So obviously, with this very nice and very difficult experiment, it's possible to do that with the C0 embedding, since you have this bending. But can you do that in a more regular way? So this is a very old question which has been raised by Nash and Cooper. Most of you know this question. So the first observation is that it's not possible to expect some C2 embedding, because if it was possible to embed the flat torus in R3 in a C2 way, then since the curvatures are preserved by an isometry, then this object should have everywhere zero curvatures. But this is not possible, because if this object is bounded and smooth, C2 smooth, then just consider a tangent exterior sphere, and then you have a contradiction with the fact that you should have zero curvature everywhere. Okay, so C2 is a bound, and this question has been answered by Nash and Cooper in almost the same time. And the theorem is the following. So it says that if you have a compact Riemannian manifold, then it is possible to find an isometric embedding which will be C1. So the only hypothesis that you have is that you must be able to embed the manifold in a strictly short way, which means that essentially the curves on the surface are transformed into curves which are smaller. And what is striking is this C1 regularity. Remember the bending of the piece of paper on the previous slide. And what is really striking also is the fact that you can do that in the neighborhood, in every epsilon neighborhood of your strictly short embedding. So let me explain why it is a little bit striking. For instance, a consequence of this theorem is the fact that you can isometrically embed a ball of radius which is of radius strictly less than 1 into S2. Okay, so you can do that in an isometric way, preserving a C1 regularity. Okay, so what was the approach of Nash and Cooper, or more precisely, what is exactly the problem? So here in this drawing, which again is taken from slides from Boris Thibert, you have your flat torus, and you have curves, closed curves in the flat torus, and you see that with the naive embedding, all these curves, which are supposed to have the same length, are transformed into curves with different length. So the question, so this is not an F, this is an F0. Huh? So the question is how to modify this F0 in order to get closer from something which is isometric. So this is not very difficult, and at least intuitively, but then you have all the technical details. So Gromov introduced a very general approach, which in my very naive words can be formulated in saying that you just have to add oscillation, but oscillation very carefully. So again, one more picture. Here, the one of these curves is too small. So what you can do is to transform a little bit, to perturb a little bit your embedding in order to increase the length. So here you come back to the hypothesis of the fact that F0 was strictly short. That is, all the curves were strictly shorter than the length the expected length. So you are allowed to increase a little bit the curve and get closer to the target length. Okay, so this is the very vague idea. And the complete formalism of Gromov is the so-called convex integration. So unfortunately, I think I will not have the time to give you all the details, but of this 1D example, but let me just stress this very nice paper of Vincent Borrelli, which deals only with the one-dimensional case, but I think that is give you really the flavor of what is exactly convex integration, which is exactly what I try to explain with my naive words in previous slide, which means that try to perturb the curves and to increase a little bit the length without without going too far, and do that step by step. And then you by Gromov's process, you can converge to an object which will be of C1 regularity. Okay, so this is very vague. I'm sorry to go through this so fast, but otherwise I will not have the time to explain what I mean. Okay, so now the great result of this HEVEA'sproject project. So this was a Grenoble project, which is the region I'm here, where I am in France. And here you have the guy of the project. Originally, it was led by Vincent Borrelli, Francis Lazarus, Boris Thibert, and Romer. And you have this web page of the project, which is very cool. You have plenty of publications, of articles, and also illustration of what they obtained. So what did they produce? So they follow Gromov's construction and try to carefully analyze what can be implemented to follow this construction, and in order to approximate a C1 regular embedding of the flat torus. So let me show you the picture that they get with this process, this iterative process. So they have 4 steps. They had 4 steps that they call corrugations. So this is the standard embedding of the torus. So they add oscillations, and oscillation to oscillations, and so on, and so on. And finally, so this is very nice. And finally, they get a global picture of what is an intermediate step of Gromov construction. Okay, so this is very, very cool. And I remember that 10 years ago, Michel Pierre, who is a colleague in shape optimization, told me, okay, there should be some shape optimization problem which are not directly related to this construction, this iterative construction, and which could lead to another approximation of surfaces which are embedding of this flat torus. And actually, Michel Pierre was correct. There is a very nice shape optimization that can be solved in order to try to identify in a canonical way such a process. And this is based on Nadirashvili result. And again, this is not a result that we think. This was a suggestion of Alexander. And what was the suggestion? So let me remind you what was the Nadirashvili's result. So it's a spectral result, and which says that if you consider orientable surfaces, what is very important is that you restrict your attention to surfaces of genus 1. So you normalize the area, then you are able to maximize the first non-trivial Laplace-Beltrami eigenvalue. And this, the maximizer is known. It is the flat torus, which is the only one which maximizes this quantity. Okay, so here, this is a little bit different. I'm sure you all have in mind this kind of picture. So here, in the previous slides, I talked about the flat torus. Here we have something which is very similar, which is not a square with periodicity, but you can play the same game with parallelograms. And in that way, you obtain different manifolds. And the one which is optimal for the maximization of this the first non-trivial Laplace-Beltrami eigenvalue is the equilateral parallelogram, which means that it's the union of two equilateral triangles. Okay, as you all know, as many knows, of course, you can associate to all genus 1 objects a conformal class, and all parallelograms with this periodicity parametrize all the conformal classes of genus 1 objects. Okay, so this is the starting point. And why it is a starting point to obtain an isometric embedding, but it's the following observation. Just have in mind Rayleigh quotient, which is the way to compute eigenvalue by essentially the ratio of the L2 norm of the gradient squared divided by the integral of the function squared. So this Rayleigh quotient only involves the derivative of functions. So it means that if you have a bijective mapping, which is C1, then the Rayleigh quotient do not change from one surface to the other. And so it means that if you are able to, if you consider an embedded surface of genus 1, of course, and you maximize in R3 its first non-trivial eigenvalue, you may expect to identify an object which is asymptotically isometric to the equilateral flat torus. So there is some kind of unicity in this vague statement that we were not able to prove. But this was the idea of Alexandre, which was a wonderful idea. Now I want to explain in 5 minutes why it is non-trivial at all. Usually, approximation is simpler than theoretical result, but here it's something which is a little bit subtle, because remember the case of the C0 embedding. We want to find an object which is close to be a C1 embedding of the flat torus. So you could say, okay, I will not be exactly this C1 embedding, but I will be very close from this. But then you can take the bent piece of paper of my first slide. You can just smooth a little bit the bending, and then you obtain something which is of regularity C infinity, and which is very close to have the same distance properties. So you see that it's very tricky from the approximation point of view to identify the good question, because you do not just want an object which is close to be the embedding of the flat torus. You want to generate a sequence of surfaces which converge to an object which is C1, and you want to have a control on this regularity, okay? And so the smoothing of the bending of the piece of paper, of course, leads you to something which is only C0. So this is a little bit tricky from the numerical point of view. And what is very cool in the idea of Alexandre is the fact that you may expect that maximizing the first eigenvalue give you some kind of control of the limit regularity. You may expect that putting some irregularity in the surface will not optimize the first eigenmode. So this was the idea, and let me just explain in a few slides what we did. So we started with the very standard parametrization of a torus, which is of course not isometric to the flat torus. And we defined some degrees of freedom, which are just this coefficient of these Fourier expansions. And we wanted to optimize this coefficient in order to obtain a larger, an optimal and maximal first Beltrami eigenvalue up to normalization. So you all know how you can compute the eigenvalue. You just compute the metric. And here, just a remark from the numerical point of view, there is something which is a little bit unusual, is the fact that the differential operator here depends on the space, on the point where you are, okay? So this is not the same operator everywhere. You have some weights. And so it's a little bit the numerical techniques that you have to consider in order to be very precise are not exactly the same, and they are a little bit more complicated. So here we consider 1D spectral collocations, and just have a look to the discrete system that we have to solve. Okay, so this is a generalized eigenvalue problem that we have to solve. So here I just forget about what are exactly the matrices. You have to solve this kind of problem. And what is important is the fact that the matrices A B, and of course the eigenvalue and the eigenvector all depend on your parameters. So if you want to do some optimization, you need to be able to compute the derivative of the eigenvalue with respect to your parameters. So you differentiate formally like this, and what you obtain is something like that. Okay, and so this was one of the first difficulty that we had to solve in order to use our optimization process, is to be able to compute this kind of thing. And this is a little bit complicated because here you see that you have to be able to compute the derivative of the matrices with respect to the unknowns. And this could lead you to a huge amount of computation if you are not very careful. So this is one of the first things that we were able to solve. And let me just say very, very quickly that we solved this problem of computing this derivative analytically, let's say, at a discrete level, in applying a coloring of the graph of the connectivity of the points on the surface, and in doing some finite differences only for every color, which makes it possible to compute the gradient we were interested in almost analytically. Okay, so this was just a technical detail, but which could perhaps interest people who want to play with this kind of tools. Okay, so now let's switch to our results, and you will see that they are very modest. So here I start with the torus, and I represent the first 6 modes, and you see that normalized modes, and you see that we start with 10.7, and then you have multiplicity 2 for the first mode. And then you have the increasing sequence. So let's look at the evolution when you apply this gradient flow on the surface. So you see a kind of enlargement of the surface. And then after 50 and 100 iteration, you see the oscillation that appear. Okay, so you will not see a lot more. And let me just say a few comments on this final illustration. So you see that the multiplicity now is close to be 3 or 4. You see all the oscillations. What is nice is that this was not parameterized in our model. I mean, in Gromov's construction, it is written that you will generate oscillation on the surface. Here, this appears just by the maximization process. So this is quite cool. What is not cool is the fact that we are very far from the optimal value, which is 45.5. And this is explained by the fact that it's very complicated, and we were not able to do that. It's very, very complicated to preserve the accuracy of the computation of the eigenmodes and playing with this kind of singular object. So we were not able to go farther than these values. So we obtained the high multiplicity as expected, and we observed that the conformal class of this profile were close to be like a class of some parallelogram, but it was not so clear neither that it was exactly the class of the equilateral triangle, equilateral parallelogram, excuse me. Okay, so it was not.
Bart, can I ask a question?
Yes.
So is it possible to actually converging to a square conformal class?
That's a nice question. So yes, when you see the values, you can think to that. Actually, this is why we had a look to the conformal class. And when you have only one deperturbation, let's say radial perturbation, you know that you stay in the classes of rectangles. Okay, but we observe numerically that usually when you have perturbation which are in both directions, longitudinal and radial, then it's pretty rare to converge to an object which has a conformal class which is closed from a rectangle. It's really a parallelogram. Okay. I don't know if so. It's possible, yes, but in this case, we had a post treatment to check what was the conformal class, and the conformal class was not the one of a rectangle, but was a conformal class close to the parallelogram. Did I answer the question?
Yeah, it's just that for this sequence of numbers really looks more like because the multiplicity, you expect multiplicity 6 for the equilateral, not 4.
Yes, but yes, I know that.
Okay. Thank you.
You're welcome. Okay, so I just want in one slide to say what we tried, because we tried a lot of things and during a lot of years. So Alexandre is still a friend of us, but we paid a lot of attention to this very nice formulation, but it was very, very good to obtain a nice numerical results. So what we obtained also is a nice way, a naive way to parametrize recursively surfaces with very few parameters. So let me illustrate what we tried. So here you obtain objects which are very nice and very close to be to the kind of objects that has been introduced by Gromov, and perhaps I can show you a more precise illustration of this. So you see here, only with 5 parameters, you can generate this kind of surfaces, which is not a big surprise. But the problem is that we were not able in these small classes we were not able to identify surfaces which provide a very high first eigenvalue. Okay, we also work on the problem of self-intersection, and we had a nice formulation based on Voronoi cells. I will not give you the details. Again, the main difficulty is to be able to play with irregular objects and preserving the precision of the spectral evaluation. And a little bit related to the question that I just answered is how far can we go with the 1D profile? Okay, so this was not a complete disaster, a fiasco, but what we tried next on the connection between minimal surfaces and Steklov eigenvalues was a little bit more successful. So let me recall you the framework. So here I will switch to, so previously we were discussing Beltrami eigenvalues, Laplace Beltrami eigenvalues. Now I have a manifold which is compact connected with a boundary, and so I will consider Steklov's eigenvalue problems. And so this is the very standard eigenvalue problem. And so you have the Laplacian Beltrami inside the domain, and on the boundary you have the normal derivative condition, which has to be proportional to the function. Okay, so then you have an increasing sequence. So let me just stress on the fact that for me, sigma 1 is the first non-trivial one. So of course, sigma 1 depends on the surface and on the metric that you have on the surface. Okay, so this is very classical. And so 1 or 2 years ago, we learned we try to learn this connection between minimal surfaces and optimal surfaces for Steklov eigenvalues. And we learned this result in a very nice paper of Fraser and Schoen. At first, we were a little bit frightened because we were not sure. We are not so we have not such a great expertise in Riemannian geometry, but this paper was very, very nice to read with my colleagues, and we understood a lot of things reading this result. So what is the question we looked at? Is the maximization of Steklov eigenvalue. So here the maximization is on the metric, and you maximize the product of the eigenvalue times the length of the boundary with respect to the metric, of course. And what will be fixed is the number of the boundary component of your surface. And you want to have a look to the optimizer of this problem. And so in their paper, Fraser and Schoen proposed the following theorem. I restrict here to the case. There are many results, I'm sure many of you know this better than me, but I will focus on the case I equal to 1, which is the first eigenmode, and on the genus 0. But I will consider a different number of connected components. Okay, so now the first observation and the deep observation is that this maximization problem has a solution. And this is a very difficult part. So it has a solution. And what is not trivial also is that the optimal eigenspace is of multiplicity 3. And additionally, you have the following results. In this space of dimension 3, you have a selection process of eigenfunctions. So you can select U1, U2, U3 in this eigenspace such that the triplet composed of U1, U2, U3, which is defined on your surface, sigma, go into the unit ball of R3 and is a conformal immersion. And the image is a free boundary minimal surface in B3. So this means that, okay, you go from your surface to the ball, and you are minimal in the sense that inside of the ball, you are minimal in the sense that you have a mean curvature equal to 0. And also, the boundary of sigma is transformed into a piece of boundary of your minimal surface, which is orthogonal to the boundary of the sphere. So there is one surface, one well-known surface, which is minimal in the unit ball of R3, which is the catenoid, which corresponds to two boundary components. And so there is, so of course you can consider a family of cathenoid by changing the 8 of the circles, but there is only one which arrive orthogonally to the sphere. Okay, so here this is the answer. So the catenoid is proved to be the optimal surface to previous problem for again genus equal to 0, 2 boundary components, and that's it. And but the result of Fraser and Schoen is of course really more general, because it ensures it proves that you can have this, you can obtain an optimal surface, whatever the number of boundary components. And now the question is how these minimal surfaces look like. So this is not so obvious at the first sight. So what we try is to approximate these minimal surfaces. So let me just first, for people who are not expert of this question, because for me it was very cool again, but very surprising, the fact that you have this link between this 3-dimensional eigenfunction space and the unit ball. So actually it comes from relatively simple consideration. So where does this minimal surface and B3 comes from? So obviously, if you consider this vector, it is harmonic, coordinates by coordinates. Now there is a first point, which is not so trivial, which is this equality. So let me remind you that since you expect a multiplicity of order strictly than 1, you are in a case where your functional is not differentiable with respect to your perturbations. So it means that you are in a non-smooth context. And so the equality, the over-determined equality that you have in this assumption tells you exactly something which is very similar to Lagrange multiplier theorem in the following sense. So the one on the right is essentially play the role of the derivative of the length. And what what is on the left of the equal sign is a combination of directional derivative. So this equality can be understood in the following way, just by saying that the gradient of the constraint is contained in the subdifferential, because you are in a non-smooth case of your functional. And the differential of the functional, when the eigenvalue is simple, involves this u1 squared. Okay, so this is a little a shortcut to understand perhaps more quickly where this equality comes from. Okay, now there is a simple fact, which is the orthogonality. Because if you just look at the derivative of your vector with respect to the two variables on your surface, which are x and y, and then you obtain that dxu and dyu on the boundary of the surface contain the position, which is exactly the normal vector to the sphere at this position. So with this, you are sure that the tangent space contains the normal direction, which is exactly the optimality, the minimality with respect to this boundary in the sphere. Now, harmonicity is not enough to parameterize a minimal surface. So to obtain the curvature, mean curvature equal to 0, you need to obtain you need to use the optimality condition in another way. Yes, so excuse me, I forgot to tell you, in the first consideration where I deduced the equality u1 square plus u2 square plus u3 square, I was considering optimality condition with respect to the conformal factor. And so the optimality with respect to the conformal factor gives you this equality. But now if you want to obtain the fact that your parametrization is conformal, then you have to use the optimality condition with respect to the conformal class, which is a little bit more complicated from a computation point of view. Okay, and then since the sum of the square is surharmonic by the maximum principle you are containing the ball. So here, this is essentially why you can observe minimal surfaces in the ball. Okay, so now we want to approximate this kind of object. So we need to first parametrize all the conformal classes. And so why we wanted to do that? Because we didn't want to play with a field of matrices, because field of matrices, this field of matrices has to be of positive and definite matrices, and this is very tricky from a numerical point of view. So the idea was, can we first parameterize the conformal classes and then optimize the densities, the conformal factor, excuse me. And so how we did that, we used this theorem, which is a relatively standard extension of Riemann mapping theorem, which says that if you have a non-simply connected set with many holes, you can map this set in C in a conformal way to a unit disk with holes which are disks of different radii and different centers, of course. Okay, so this is a generalization, and in our setting, it means that we only have to. So this is just excuse me. Yes. So this is the way we used to parameterize the conformal classes. So it means that we did our optimization in the class of disks with holes, with the fixed number of holes, which corresponds exactly to the B-1 circular holes, which is where B is the number of boundary components of your surface. And on every circles, we had to optimize a density which corresponds. So this is what you have in this red rectangle. You have that through this mapping, this conformal mapping, there is a factor which appears into a Stekeholder eigenvalue problem, which is just in front of the eigenvalue. So now the eigenvalue problem is transformed into a very simple one, which is just, so I will skip this part, perhaps I will come back later. But now The problem we have to solve is to solve the Steklov problem, the usual one. I'm looking for harmonic function into my disk with circular holes. With this specific boundary condition where rho is fixed, it is my density, my positive density along the boundary, okay? And so what I am interested in is to maximize now the product of the eigenvalue I'm considering times the boundary measure. And so my parameters are the disks, the circular holes, the centers and the radii, and also the density along all boundaries. So this is very nice from a numerical point of view, because what we have to optimize is only one dimensional. You see, the densities we are trying to approximate are only defining along the circles, and this is not too demanding from a computational point of view. Okay, so now we want to do some optimization, but then to optimize something, we have to compute the derivative. So we compute, as I told you, we compute the derivative of the eigenvalue with respect to the conformal factor, which is represented here by this density rho, and also with respect to the center and the radii. So let me just say one comment. So here we obtain exactly the same formula as El-Soufi previously, and Fraser and Schoen and many authors when you compute the derivative with respect to the conformal factor. But here we have different formula because we have a different parametrization of the conformal classes regarding the sensitivity with respect to the radii and the centers. Okay, so now I just want to explain why this multiplicity of multiplicity 3, which is expected, creates some difficulties, and what can we do to play with this kind of non-smooth problem. So here I just explain how we can obtain some optimality condition in the non-smooth setting, because here just previously this formula are only correct if you are considering simple eigenvalues. Now what happens if you are multiple eigenvalues? So this is classical in perturbation theory, that you can parametrize your eigenvalue in another way. So from a numerical point of view, this is the picture that you have in front of you. You have different value, so you perturb your density with some parameter in some way, in the way you like. And if you have a multiplicity, let's say 3, you have this kind of curve which says that you are not able to parametrize these curves, at least in practice, without more information. So here the picture we have in mind is the following. That is, what we would like to have is something like that. But if you numerically, we have never this information, because it means that you know that before the multiplicity 3, if you are considering first, for instance, the brown curve, you know that the number of the brown curve corresponds to the third eigenvalue, and then it's switched to the first one. Okay, but you never know that. So it's very difficult from a numerical point of view to play with this switch of curves, let's say. But from a theoretical point of view, this is not a big deal, because with this information, you can just, with these smooth curves, you can compute the directional derivatives and compute this quadratic form, and you will be able to characterize all the eigenvalues, and you will be able to obtain this over-determined condition. So let me just give you a flavor of the proof. So you want to be able to prove that you can have a sequence of eigenvalues. So here I'm in the multiplicity equal to P. And I want to prove that it's possible to select P eigenfunction which satisfy this equality. So you consider this convex domain. The convex generated by the square of the eigenfunction in all the eigenspace you are considering. And the question is, does one is in this convex set? So you can apply Banach theorem. If it is not the case, then you may have these two equalities. So the first, because you have an hyperplane which separate the convex K and the singleton 1. So it says that the perturbation along the boundary is strictly positive and the derivative are negative. And so it means that previous quadratic form which give a description of all the derivative as non-negative eigenvalues. So you do not know what are the derivative of these smooth curves, but what you know is that if it is the case, then it's possible to perturb the domain such that, perturb the metric such that you obtain a product which is greater than the original product, which is a contradiction, okay? So just this separation argument gives you this equality. Now, I would like to give you the description of our approximation framework. So we use the theory of harmonic functions. So you may know that if you consider analytic function, it's possible to approximate analytic function by rational function, which have poles in the complement of the domain. Okay, so this is a very well-known theorem due to Runge. So here I have an analytic function, and I am able to produce such an approximation. And what is interesting is that in this theorem, you are allowed to fix the poles inside of the connected components, okay, of the complement. But here with Stekeler problem, we are interested in playing with harmonic function. And there is a generalization of this theorem, which says that now if you are not interested in analytic function, but you are interested in harmonic function, it's not exactly the same game. If the domain is simply connected, everyone knows that every harmonic function in the domain is the real part of an analytic function. But this is not the case. This is not true anymore if you have a domain which has some holes. If you have some holes, then every harmonic function, remember that I have in mind eigenvalues, eigenfunction of Stekeler problem. So if you want to parametrize harmonic function, then you, as expected, you can say that it's the real part of an analytic function in the domain, but you have to add singular parts, which harmonic parts, of course, which are the logarithmic contribution of poles in the complement, again, of the domain you are considering. So perhaps this small drawing is more clear. So here my domain that I'm considering is this one. So I can fix poles and say that every harmonic function in my blue domain is the sum of the real part of an analytic function plus logarithmic term. So I will not detail the proof. This is very simple, but I like this proof. This is why I put that here. But let's stress now on the approximation. So what is interesting now, see how can I approximate in a very precise way Stekeler eigenvalues. So based on previous theorem and Runge theorem, the idea is to try to approximate an eigenfunction as a linear combination of real and imaginary parts of functions in the space B. Okay, so I'm just saying that I will try to adjust the coefficient of my series, which will be composed of real parts and imaginary parts of power of Z, and positive and negative, logarithmic term, and Laurent terms. And I will adjust this coefficient in order to be close to from an eigenvalue, from an eigenfunction. So here, this is the space of approximation. And I will look for a function u in this space. And now I would like to, so of course, every function u in this space is analytically harmonic, whatever the coefficients. But what is not satisfied is, of course, the boundary condition. So how can I fix this? I will sample the boundary of my domain, and I will impose the equality normal derivative equal to sigma rho u pointwise all along the red points of sampling of my boundary. Okay, and so this gives me again a generalized eigenvalue problem, which again depends on my parameters. But this is, let's say, now standard. I can solve this. Why we choose this method and not finite element method or boundary integral method? Because we expect to have many very, very small holes in our domains. And so we thought that we needed a very high precision. And let me show you which kind of picture we have. So here I took a disk with four holes, excuse me, circular holes. And on the right, you have a log plot of the evolution of the approximation, of Steklov modes. And you see that with respect to the maximum, the highest power that you are considering in the B space. Okay, and you see that if you just consider m equal to 8, which is relatively small, then you have stability and you obtain a precision which is the precision of the computer. Okay, so this method, when it converges, it means when you are able to produce enough terms of this space of approximation, provides you a very, very high precision of your approximation of the eigenvalues. Okay, so perhaps I should go through the theoretical details. Now, I'm not only optimizing the density, but I'm also optimizing the disk. So, of course, the disks do not have to overlap, and they do not have to go outside of the unit disk. So you have to impose some nonlinear constraints, but very few with respect to the degree, the number of degree of freedom we need to approximate the density along the boundary. Okay, and here, as I told you, one big difficulty is the high multiplicity of the eigenvalue, which is expected, of course. Then to transform this into a regular optimization problem, but now constraints, we just play this standard trick by introducing a new variable and adding these constraints with respect to the eigenvalue we may suspect to be of multiplicity greater than 1. Okay, and this is the picture we obtain. I will show you more precise picture in a few minutes. So, but what I want to show you first is just the geometry of the points. So here you have the optimization. So it's the result of the optimization of the first Steklov eigenmode with 2, 3, 4, and so on boundary components. Okay, so here you do not see the optimization of the density. You only see the circles. But you can look at the scale and see that the circular holes are very, very small and have a very regular positions. And this was only possible, I mean, we were only it was only possible for us to reach such a precision with the approach I just presented. Okay, and here are the surfaces that we obtained with 3 boundary components, 4, 5, and a larger number. And as it has been observed by Jean and Alexandre, you may observe that boundary components can be spread all over the sphere, and not only on diameter, which was one of the questions raised by the people involved in this nice story. So let me show you now more precisely what we obtained. So here we were able to recover the catenoid, the critical catenoid. So here we started from a disk on the right, and we optimized, and we obtained this new disk. And okay. And here you see the value that we obtained. You see that up to 1, 2, 3, 4, 7 digits, we were able to obtain the equality of the first eigenmode. So sorry, it's written lambda, but of course it's sigma. So you see that it's very, very precise, and as expected, of course, the eigenspace is of dimension 3. So let me switch to a surface which was not described analytically, which is the one related to 3 boundary components. So here, again, the optimized circles. Here you see the optimal densities. So you have the density on the exterior circle, the densities on the interior disks. And here is the object. So this is the minimal surface, which is obtained by the maximizing of the first eigenmode. Okay, and since we have an analytic representation of the parametrization, we are able to check if we are far or not from being of zero mean curvature. And this is what we did. And you can see here on this colorized plot that up to the 3 digits, we are of zero curvature. And let me stress that you have very high curvature in some places, you can guess. If you have a look to the mean curvature, to the Gaussian curvature, of course, the picture is very different and you have very high values. Okay, and so it was possible to play that game with many different, with different number of boundary components. I don't know which one I can show you. So here you have a different configuration, the different densities. Okay, this is traces of the eigenfunctions. And here you have the shape. And to conclude my talk, I would like to show you what we obtained with when maximizing the 3rd eigenvalue. So again, we obtained a multiplicity 3, and we obtained this picture. So this is this one. So this is the surface we obtained. So here you have self-intersections, but still you are very close to be of zero mean curvature. So let me show you that. So you see the values, and if you want to see a more precise illustration, I can show you the effect of the mesh, because here we have a mapping, a conformal map, which preserves the angles. So here you see that this is the same surfaces, but you can guess that the angles are preserved. And okay, and this is the end of my talk, and I thank you for your attention.
Thanks a lot, Édouard, for this talk. If anybody has any questions, you can either unmute yourself or ask your question in chat, and I'll relay it to Édouard.
Can I start then?
Yes, you can.
So the question is, so have you tried looking at the distribution of holes on the sphere instead of the disk? Because they seem, because by like Jean and Alexander results, they should be kind of equidistributed on the sphere. At least you expect them to be equidistributed in the sphere, and on a disk it doesn't quite give it justice, I guess.
So yes, so we had this idea to work on the sphere instead of the disk after we obtained the first results. So we were a little bit too lazy to switch to the sphere case, but that could be nice. So no, I do not know. So I do not expect homogeneity of the radii, perhaps of the centers.
Sure, but at this point it shouldn't be too hard, right? You just take stereographic projection.
Okay.
And
just
see
use our results and just report. So we didn't do that. We should, yes. So thank you for the suggestion. Yes, we should do that.
There's some freedom, of course, still remaining because you have stereographic projection.
Yes.
And then you can like do a Möbius transformation.
Yes, but perhaps we can manage it to, let's say, to optimize the homogeneity and see what we can produce.
Yeah, you should expect to have like equidistributed centers and then almost the same radii.
Yes, yes, yes.
Perhaps if I can say something on the sphere, you could have different conformal factors that are isometric to each other's. So you could approximate the same maximum using different type of holes with the it will not necessarily be equidistributed if you take a different conformal factor to start with.
Yeah, so what I'm saying is that you need to optimize a little bit by Möbius transformations afterwards, after the stereographic projection.
Maybe I can ask a question. I was just wondering, in your plot where you showed the error, how do you evaluate the error? Did you compare with another simulation that was run for a longer time or something like this? I'm not a numeric person.
Yes, you are right. So no, we evaluate the error by taking a huge number of elements in the series. And at the end, so by taking, so this is, and we approximate the eigenvalue in this very, very refined space. And what we can see is that only the very first play a role. I mean, have a coefficient which is not very, very small. Okay, so to answer the question, in order to have a reliable value, which we identify to the true value, we use a huge amount of basis functions. So here I played with a maximal power of 8, and I think that to have what I used for the optimal value, I think I used something like 50, a power of 50 at most. So a factor of 5.
Can I ask another question?
Yes, you can.
Have you tried to, like in the first part where for the torus, have you tried to run the optimization simulation for next eigenvalues, not for lambda 1, but for another one, to see what happens?
No, we didn't.
So I have two questions actually. The first one, so when you have these surfaces with self-intersection, when you try to optimize for a higher eigenvalue than the first one, right? Did this happen every time you tried to optimize for a higher eigenvalue, or it was sometimes you actually got something with no self-intersection?
Yes, I was too fast on this point. So yes, I know that, and we observed that the value we obtained was not globally optimal. Mm-hmm. So we suspect that it's only a critical point or a local minima.
Okay.
Okay. And the point is that this was in one of my slides at the beginning. The point is that the optimal one, for instance, for sigma 3, if I remember well, is suspected to be the catenoids union with a sphere.
Mm-hmm. Yeah.
I think. And if it is the case, in our parametrization, it means that if you want to be able to approximate this kind of singular object, singular metric, then your density you have to consider have to be, yes, very, very singular. And since we were playing with Fourier series with bounded coefficients, it's exclude this kind of singular profiles. So this is why we obtain more easily this self-intersecting surface. But let me say that this surface is very stable from the optimization point of view, in the sense that the associated conformal factor is very smooth, and the configuration of the circles are also very, very stable.
Okay.
Can I ask a question?
Yes, by all means.
So maybe it's not quite about optimization, but about like the space of all embeddings of a surface into a three-dimensional space. So there were some old papers by Frank Morgan, who kind of started off with a minimal surface spanned by a random closed curve in dimension 3, and then so he just said, okay, if x, y, and z coordinates are just 3 random Fourier series on a circle, and then let's dip that into SOAP and look at the minimal surface with that boundary, right? And then he said, okay, so then instead of having functions on a circle, we could have functions on a torus or on a sphere or on some surface. And so we just parametrize the x, y, and z coordinates if we want to embed in R3 by 3 random series of functions, and random with respect to some background metric on a surface. And so is it interesting to ask, like, so you in practice, you put some kind of measure on Fourier coefficients and you work with that. Is it interesting to see, like, how far will such a random thing be far? How far will it be different from an isometry, this random embedding? So this is maybe not about, you know, optimal solution of some problem, but about kind of generic case. How far is generic case?
So I do not know this this process. So it has been proposed by Frank Morgan, you said?
Yeah. It was published. So here, Curves in Space is 1978, and Spaces of Surfaces in 1982. So these are fairly old papers, but it's a way of just parametrizing maps from a manifold into Euclidean space using just random series of functions. Mm-hmm. And so in some sense, when you try to optimize, you are kind of also working with some series of functions. So I guess the purposes are a little bit different. But is it interesting to see how generic case differs from what you expect, sort of expected distance from a random to the optimal, mm-hmm. in some sense? I don't know.
Okay, thank you. I will have a look. We didn't.
I can send you a reference if you want.
Yes, you're welcome. Thank you very much.
Absolutely. Okay.
I have another question. So in the paper, you have a very nice observation on position of the centers.
Yeah.
Can you maybe comment on that? I think it would be interesting maybe for other people as well.
Yes. So it's yes. We try to make a link with some regular configuration of Thompson's problem. No? This is what we are thinking too.
Yeah.
And so, but let me say that, yes, we try to see where the centers of the boundary components were located, and did they exhibit a specific configuration. So for small numbers of connected components, we observed sometimes that we were able to regular polytopes, and we observed also some kind of homogeneity which have been observed in different functions. But perhaps I would give a warning in the sense that it's not completely clear how to define the center of the connected components, because for instance, if you have in mind the optimal surface with 3 boundary components, the boundary components are not circles for sure. And so what is the center exactly? So we took the center of masses and tried to look at this, the regularity of this configuration, and to point to some well-known configuration on the sphere. But for me, the first question is why to consider the center of mass and then project on the sphere? Why? It's not completely clear. So if you have if some of you have some ideas of what could be interesting, and which which quantity represents these boundary components, I would be very happy to discuss that.
So I think in the paper you're mentioning some sort of discrete optimization problem for the energy.
Yes.
Right? So,
yes, which is only related to the centers.
Right. So you don't think that's interesting enough to justify the taking center of mass?
I just say that it's not canonical. I mean, there is a choice here. So I don't know if it's the good one. And then if we choose the good one, so we tried with this one to play with a discrete optimization problem, but we were not sure we choose the good one.
Are there any other questions for Édouard?
I have a very trivial question. So what did you use to do the rendering of your surface? They're really nice.
You must do some ray tracing.
Yeah, but which, I know, but which, is it Povray or something like this?
Yeah.
Oh, very nice. Okay. Thank you.
And anything else? All right. Well, if not, let's thank Édouard again for this talk. We will reconvene next week, same time, same place, with a talk by Simon Larson, who will speak to us about two-term spectral asymptotics for the Dirichlet Laplacian in a Lipschitz domain. So see you all next week, and thanks for being here.
Merci, Édouard.
Oui, ça va? C'était intelligible?
Oui, tu as été très généreux avec moi. On a parlé de ça 10 minutes en 2012, si je me souviens bien.
Mais oui, mais moi, j'avais trouvé... Non, mais après, j'ai été trop gentil parce qu'on a souffert à cause de toi. Non, mais ça a été l'horreur, cette histoire. Hein. Je n'ai pas assez insisté, mais on a bossé comme des chiens pour avoir ces quelques heures. Et c'était très frustrant. Donc, non, mais l'idée, moi, je l'ai trouvée géniale. Hein. Mais malheureusement, voilà. Tu les as donnés aux mauvaises personnes.
Bon, en tout cas, je n'aurais pas su comment faire non plus.
Bon, messieurs.
Bonne journée.
Je vais me coucher, là. Allez.
Ah, bonne nuit, oui.
Salut. Non, pas encore tout à fait, mais bientôt. Salut.
Ciao, ciao. Ciao, salut.
Au revoir, à la prochaine.
Merci.